This is lecture 18 of CS47 computer organization study. In this lecture, we'll look at the addition subtraction circuit. I'd say specifically addition subtraction logic circuit. As I told earlier, that a computer or a processor doesn't know anything about arithmetic addition, subtraction, multiplication, division. All it knows is basically logic. It's a logic crunching machine. So we'll see that how that logic crunching we can use to make arithmetic addition subtraction for integers. Okay, so we'll concentrate on the integer part of these operations. So to do that, we need to understand this binary addition process. Okay, as everything inside computer is represented as a binary values. Values are represented as binary format. So we need to know how this binary addition subtraction works. Okay, let's start with the addition. So let's say there are two binary variable A and B, and if we sum them up, any sum process produces a sum and a carry. Like if you think of your decimal addition process, like 2-digit, let's say you are adding up 8 and 3, right? So 8 plus 3, its sum digit is 1 and carry digit is 1, right? So similarly for the binary, if you add 0 plus 0, its sum is 0, carry is 0. 0 plus 1, sum is 1, carry is 0. 1 plus 0, sum is 1 and carry is 0. Only for 1 plus 1, your sum bit is 0 and carry bit is 1. So you can well imagine why, because 0 plus 0 is basically a 0, right, in a value. 0 plus 1 is a decimal value 1 as well, right? So this is like your sum bit becomes 1 and your carry bit is 0. Whereas your 1 plus 0, which is decimal value also 1 and 0 is 0. So your addition result is ultimately 1 where carry is 0. But 1 plus 1, so if you think of the decimal value corresponding to bit 1, it's also 1, right? And 1 plus 1 in the decimal is 2, which is represented as 1 0. So that's why your sum bit for that addition 1 plus 1 becomes 0 and carry bit is 1. Now if you think of this summation process, right, you notice that this like 2 bit of addition gives you 1 sum and 1 carry. So if it is a 2 multi-bit operands, what happens to the carry? Okay, to understand that, let's try to do one arithmetic operation, arithmetic addition. Let's review that one. Let me open up a new text document and let's say we are adding up this decimal value to, I'm just writing 2, 3, 4, 5. Okay, let me just make a space there to separate out different digits of. This is 2345 plus 8000, maybe 984. Okay, so we're trying to do an addition there. Okay, and let's make some space here so that okay. So here what we do, we are trying to do an addition. Okay, so we take these 2 digit 5 and 4, right? So we add them up and that become your 9, right? But okay, 9, okay, and there is no carry from here. and then this is 8 plus 4, which is 12, means I have this carry, sum 2, and my carry is 1 in this case, right? And then for the third digit, we do 9 plus 3, 12, plus 1, 13. So 3 and carry become 1. And then for the fourth column, now we add 8 plus 2 plus 1, which is 11, and carry become 1 in this case. Let's say, just to make sure we understand this, the carry is 1 for the fifth column now, because our summation is carrying forward, and then we make 1 here. So our addition result become 11,329. But now see what are our underlying assumption is. Like 5 plus 4 for the first column is 9, which means I can well imagine, just to make the process uniform, that our carry for the second column is 0, right? 5 plus 4, 9, and carry out is 0. Then we add 3 digit here. 0 plus 4, 4, 4 plus 8, 12, that is 2, and carry out become 1, which is carry in for the next stage, and then we add them up, carry out, next stage, and here in this case we have like 0, like 2344, we can just prepend a 0, which doesn't change the value, but it certainly makes sense. Now we are adding up 3 digit here also for the last fifth column. Now only bit of non-uniformity left for the first column, right? So every other columns we are adding 3 digit, but for the first column we are adding 2. So we can, what we can do here in this case, we can imagine there is already a carry in for at this first stage, which is always 0. So constant carry in 0. So this is like a, this is carry in for carry in digit for each of these decimal places, or let's say in general columns, carry in digits. And the first one is basically your, this one is basically your default carry in for first column, right? So this is my overall process for a decimal number. We need to do the same thing. So for the binary as well. So let's say I have some binary number like 0, 0, 0, 1, 1, 0, 1, 1. How many bits are 2, 4, 6? So let's put 2 more, versus 0, 1, 0, 1, 1, 1, 0, 0. Yeah. And we are doing addition here. Okay, we are doing addition here. So like the decimal addition, we assume there is this default carry in. So this is my carry in bits. This is my, let's say, operand 1, and this is operand 2, and then we need to add 3 rows basically. So far in the slide, what we have shown is just what is the result between summing up 2 bits, right? But what I'm saying, it is not sufficient to sum only 2 bit. So let's say we start without summing the carry in bit, and let's start that addition process. So 1 plus 0, according to that that truth table we just saw, it is 1 and carry out is 0. And then next one, 0 plus 0 is 0 and carry out is 0. And 1 plus 1 is 0, carry out is 1. Now you see, I just cannot do here 1 plus 1 as 0 and carry out 1 for this guy. That will be a wrong thing, because I am not here in this case, I am not adding up the carry out from the previous stage or previous column. So we need to do something better than 2-bit addition. We need a 3-bit addition in this case. So 3-bit addition, you can well imagine this is 1, 1, 1, which is basically, if you think in terms of decimal, this is 1 plus 1 plus 1, which is 3, and 3 is represented as 1, 1. So your sum for this case is 1 and carry out is 1. Now it is 1 plus 0, which is 0, 1, plus 1, which is 1, 0. Now this is your 0 and your carry out is 1. Now we add 1 plus 1 is 1, 0, plus 0 is 1, 0, which is now give you 0 as a sum and 1 as a carry out. And then it is 1 plus 0 is 0, 1, and then plus 1 is 1, 0, which is 0 in and carry out is 1. And this is 1 plus 0 plus 0, carry out is 0 is, this is 0 from this stage like that, and which is basically 0 carry out from the last stage. And of course we can imagine there is one more 0 there, one more 0 there for the process, and that becomes 0, 0, 0. So this is what your sum would be. So now let's look at in terms of 3 bit addition. So first column, the first carry in bit is default 1, which assume this is 0. So 0 plus 1 is 0, 1, plus 0 is 0, 1. So 1 is your summation, carry out from that stage is 0. 0 plus 0 plus 0 is 0, carry out 0. Then 0 plus 1 plus 1 is 0 sum, 1 carry out. Then we go like 1 plus 1 plus 1 is sum is 1, carry out is 0. Then 1 plus 0 plus 1 is sum 0, carry out 1, 1 plus 1, and so on and so forth. So now you see we started with this 8 bits. No, not this one. These operands were 8 bit, right? 0, 0, 1, 0, 1, 1, 0, 1, and 0, 1, 1, 0, 1, 1, 1, 0, 0, right? These are 2 operand 1 and operand 2, which were 8 bit. So for an 8 bit operands, our sum has to be representable by 8 bit. Okay, you see, like in this case, in the case of decimal, we started with 4 digit and we have no issue in writing a 5 digit result, right? But in computer system, it's a problem. For example, if my computer is an 8-bit computer, means all the number can be represented in this computing system with 8-bit only. Now, if my sum needs more than 8-bit, okay, then your result won't be able to be expressed with 8-bit anymore, right? It need 9-bit, but in computing system we don't have 8-bit for 8-bit computer, so we cannot represent the result, and that becomes my overflow condition. That means it's a sum is erroneous. Let's take an example. Let's take the same similar example a little bit, and let me just copy it, and instead of, let's say, 0, 0, I had a 1 here. Then what would happen, In this process, this sum would be 0, my carry out would be 1, and my sum would be 1. So, my sum result is the entire 9-bit result, right? But point is that I'm assuming if my computer is 8-bit computer, then I can only hold this 8-bit as a result, which is wrong, obviously, for the summation result point of view. So that means this is error and I have overflow condition. So this 9th bit, what we see here, is called a overflow bit. So as long as my overflow bit is 0, I know my summation result is correct. It can be held into this 8-bit in this example. If sum overflow bit is 1, then I know my summation answer for this 8-bit answer is wrong. I cannot take it. There is overflow condition. Result is bad, basically. Think the same idea in terms of 32-bit computer or 64-bit computer. Your operands in the 32-bit computing machine, operands are expressed in 32-bit pattern. Okay, 32-bit patterns. So it might happen addition of two 32-bit value can not be represented with 32-bit anymore. It needs one more bit, as in we have seen in the 8-bit example as an one overflow bit. And that way it becomes also an erroneous result. So as long as two 32-bit addition result can be represented within 32-bit, I am okay with the summation. If it is not, I have error in result, and we check that with respect to the overflow bit. We check if it is 0, my summation is good. Overflow bit, if it is 1, then my summation result is wrong.